Hello guys, welcome back to Maison African Motives. Still working on engineering science N3. In this platform, we are given the question paper, which was written in March 2023. In this case, that is the one that we are going to work with 31 March 2023. All right, so we are not going to waste much time, guys. We are going to quickly rush through the questions that we are given. So that was the requirements, was the properties of water and steam, which means the steam table was needed. We'll see that one. Okay, so let's check what we are given in this case, our instructions, which is very, very important to note. In this case, read all the questions. Most importantly, on this one, number the answers according to the numbering system used in this question paper. All right. The others are there direct. Okay. Question number one, it was on ocean power and energy. Okay. Define on 1.1, define the acceleration of an object. That was 1 mark just to define what is acceleration of an object. So acceleration is simply the rate of change of velocity. So this one, we can just say it is, all right, it is the rate of change. So that is the rate of change of velocity in this case, all right, of velocity. So acceleration is measured actually in meters per square second. Remember that acceleration, that's velocity over time. All right, on 1.2, we are given that the graph in Fig 1 shows the velocity time graph relationship of a falling free object in this case. So take note, this is a falling free object that you are given in this case, all right? So meaning to say we are going to apply our G, which is our gravitational acceleration of 9.8 meters per square second in place of acceleration. That is what is going to happen in this case. It's a free falling object, all right? So we are given that t is equal to 0 up to t is equal to 4. That is the time from t is equal to 0 up to t is equal to 4. Use the graph to determine the value of m. So if you are to check here, the value of m is indicating the velocity at this point. This is your velocity in meters per second. We have got 16. Then we have got v at this point here. That is what this m is representing. So as we know, guys, from the formulas of linear motion, we can apply that. Remember that we can just use this space here, 1.21. That velocity is equivalent to u plus at. Remember, I said a is going to be represented by g, which is 9.8. For acceleration, it's a free falling object. So v is the final velocity, which is the same as this m that we are given in this case. So if m is representing v, our final velocity, therefore m is equal to u, which is your initial velocity. You started at 16, so this is 16 plus at, which is 9.8 times the time from 0 to 4. That is, there's a difference here of 4 seconds. So that is your time in this case. So you multiply by 4. All right, so this is what you're going to have in this case for the value of m representing the final velocity. So our m is going to be 55.2. We are going to have something like 55.2. This is velocity measured in meters per second. So take note, it's final velocity, but just it's written as m. So you're just going to have it as m, okay? So 1.21, that was it, 2 marks for that. 1.22, the displacement of the object after 4 seconds. So you want to calculate the displacement of this object. So for displacement, there are so many ways that you can actually use. Remember that displacement is equivalent to area. So you can work with the area in this case of the shape that you are given. Remember, at this point, we calculated m and we got that our m is 55.2 in this case. So we can use the whole trapezium to calculate the area. Remember that the area, so this is 1.22. So remember that displacement in this case is equivalent to area. So if it is equivalent to area, that means we are going to apply the area that is the area of a trapezium, which is half base times the perpendicular half base. So this is for the triangle. I want to combine the triangle here, but no, let me just use a trapezium as it is. Half of A plus B times the perpendicular height in this case. Then I'm going to show you a lot here. We have a lot of ways that you can do this. So from the trapezium, these are the two sides which are parallel in this case. Okay, and this is your perpendicular height at 90 degrees here. So you've got 16, and we've got this side from this point up to this point is equivalent to 55,2 in this case. All right, so you're going to use 16 and 55,2 as your parallel sides. So that means your area of a trapezium, so that is half multiplied by 16 plus 55,2 for the parallel sides times the perpendicular height, which is for the time from 0 to 4, which is 4. So this is what you're going to have. So guys, you must be very, very careful with the information that you are given. Are you working with a trapezium? Are you working with a triangle? Which shape are you working with? That part alone is very, very important. So that is what you're going to have. So here we're going to obtain 142,4 meters. That is your displacement. Or you could have worked this way, changing this here, or okay, obtaining this, which means we've got a rectangle in this case. So your displacement in this case was going to be equivalent to the area, which is now our area. We are going to have a rectangle that is length times width or length times breadth plus the area of a triangle in this case, which was going to be half base times the perpendicular height. So here we are referring to this rectangle that is 16 times 4. So we are going to have 16 multiplied by 4 plus half times the base of the triangle, which is, we are referring to this from this point to this point, the same from this point to this point, which is 4 times the perpendicular height, that is from this point to this point here. So since this is 16, from this point up to this point, you subtract 55,2 minus the 16. So if you subtract, this is going to give you 39,2. This point here, from this point to this point, it is going to be 39,2. So you subtract, so you multiply to 39,2. So that is what you're going to have. Still, you obtain the same value, which is 142,4 meters. Or you can use the formulas still of linear motion. Since we are given in this case, we have got our time from 0 to 4. We have got our acceleration. We have got the time. So we can calculate that displacement. In this case, I've got this formula that I want you to see, that displacement can be given as S is equivalent to U plus V over 2 times T. So you can use your formulas. That is, S is equivalent to U plus V. U is the initial velocity, which is 16, plus V, which is our final velocity, the one that we calculated here, of 55,2, everything over 2 times the total time, which was taken of 4 seconds. So still, you must obtain the same answer of 142,4 meters. All right, so all these guys, they were calculations that you could have used to calculate the displacement. Okay, so that was actually 3 marks for that. On 1.3, we are now given that a Toyota Yaris weighing 3.5 ton is driven uniformly from a stationary position to a speed of 72 kilometers per hour. So take note of the information during a period of 25 seconds in this case. All right. So on a horizontal road, assume that the resistance against motion is 0.1 Newton per kg. Calculate the total force exerted by the Toyota Yaris. Okay, let's just try to take the information. So we are given that it weighs 3.5 tons. That is the mass of the Toyota Yaris in this case. So this is question 1.3. All right, so let's just take our information. So we're given the mass of the car, which is 3.5 ton. So 3.5 ton we can convert to kgs. Remember that a ton is equal to 1,000 kgs. So if we multiply by 1,003.5 times 1,000 to convert to kgs, this is going to give us 3,500 kgs. All right, so we've got the mass in this case. We're given that this is taken from, it is actually taken from a stationary position, that is, there is no movement, stationary. So the velocity at that point is at 0 to a speed of 72 kilometers, which is the final speed. So we are given the initial velocity that is at when it is stationary, where there is no movement, that's 0 meters per second. And the final velocity of 72 kilometers per hour in this case, of which you can convert to meters per second, since we know that 1 meter per second is equal to 3.6 kilometers per hour. So to convert to meters per second, we can divide, since this is in kilometers per hour, we can divide by 3.6 kilometers per hour in this case. So this is going to give us 20 meters per second. So we have got our velocity as 20 meters per second. And also we are given the time frame during a period of 25 seconds. So that is the time that was taken for this process, 25 seconds. Also, we are given the friction, which is the resistance against motion of 0.1 Newton per kg, which means each kg we are being affected by 0.1 Newton in terms of the frictional resistance in this case. So that's 0.1 Newton per kg. But how many kgs do we have in this case? We are given 3,500 kgs. So that means we are going to multiply 0.1 times 3,500, which is going to give us 350 Newton. So that's your frictional resistance in this case. Okay, so every information is there. Let's take let's see the first question. The question was to calculate the total force exerted by the Toyota Yaris. What is the force? From this information, we are given that it is moving on a horizontal ground. So which means the only force that is affecting is the frictional force of 350 Newton. So the total force in this case, that is 1.31, we are going to have our total force as the, if we subtract the frictional force from the total force, we know that we are going to have the accelerating force. So to find the total force, we can transpose the frictional force to the accelerating force. So it is going to be accelerating force plus the frictional force in this case, whereby the accelerating force is the force due to acceleration. So this is going to be MA. So our force, total force is going to be MA plus the frictional force in this case. Do we have the mass? Do we have the acceleration? We have the mass in this case. We are given the mass here, but we do not have acceleration. So which means from this information that we are given of linear motion, we can calculate the acceleration. We have got in this case, we have got the time, we have got the initial velocity, the final velocity. So remember that V is equivalent to U plus AT. So that means we can calculate the acceleration because we do not have acceleration here. So V, our final velocity of 20 is equal to U, the initial velocity of 0 plus AT, whereby T is 25 seconds. So it is going to be 25A. So from there, we can calculate our acceleration. That's a 0. So we are going to subtract nothing, or 0 plus 25, that's 25A. So 20 is equivalent to 25A. So to find A, divide by 25 both sides. This can give us the value of the acceleration. So 20 divided by 25, that's 0.8 meters per square second. So I'm now having acceleration, the frictional force. So that means we can calculate our total force in this case. So the total force is going to be MA, that is mass, the mass here of 3,500. Okay, so that's 3,500 in this case. So we've got 3,500 times the acceleration of 0.8. So that's 0.8 plus the frictional force, which we calculated from the 0.1 Newton per kg, and we multiplied by 3,500, we got 350. So we are going to add 350 Newton. So that is going to give us the total force that was being exerted by this car. All right, so if we calculate properly, here we are going to obtain 3,500 times 0.8, which is going to give us 2,800 plus 350 in this case, which is going to give us a total of 3,150 Newton. All right, so that was our total force. Okay, so that is what we had, guys. Let's check the other part of the question now. It was to calculate the change in momentum of the Toyota Yaris. That's 1.2. So remember that momentum, guys, is simply the product of the mass and the velocity. So the change that is after that, so which means this one is just a product. So that is going to be mass times velocity. Remember the mass of the Toyota Yaris in kgs, we've obtained 3,500 at a velocity of 20. So if you multiply, this is going to give us 70,000. So that's 70,000 kgs meter second per second. So it's kg meter per second. All right, so that is it, guys. 2 marks for that. 1.4, we are now given that a pulley is driven, okay, a pulley is driven by a driving belt with a belt speed of 12 meters per second. All right, so let's just take our information again. So we have got the velocity of 12 meters per second. The tension in the slack side is half the tension in the tight side. Okay, the tension in the slack side, which is T2, it's a half of the tension in the tight side, which is T1. The tension of the tight side is 800 Newton. So given T1 is 800 Newton. So the question is to calculate the tension in the slack side, which is T2. So from this information, we are given from the formula or from this information that T2 is equivalent to half of T1. So if T2 is equal to half of T1, I'm just going to multiply. That is half times T1. I have the tension in the tight side of 800. So this is going to give us 400 Newton. So I have T1 in this case. T2, sorry, which is 400 Newton. Then 1.42, the power transmitted. Remember that if I have got the effective force, I can calculate the power. Since power is equivalent to the effective tension times the velocity. We have the velocity here. So we need the effective tension, which is the difference between T1 and T2. So P is equivalent to T1 minus T2 times the velocity. So that means our power is going to be T1, which is the tight side, that is 800 Newton, minus the slack side of T2. So that's 800 minus T2. We got it here. It is 400 times the velocity. That is, we have also the velocity here of 12 meters per second. So that was the formula that was best to use to calculate your power in this case, guys. All right, so your power in this case, if you calculate properly, this is going to be 400 times 12, which is going to give us 4,800 watts. So we've got 4,800 watts, of which you can convert to kilowatts if you want. That is going to be 4.8 kilowatts if you want to convert to kilowatts. This one is it's your choice, guys. It's your choice, okay? So we are not told. We are just calculate power, so you can write the units of your own choice in this case. All right. So let's check the other part of the question, which is on question 2. So the question 2 was on moments, and we are given the first part of the question to give 2 types of loads acting on a beam. So on a beam, we know that there are so many loads that can act there, but which 2 types that we have that is affecting? So in this case, we are referring to the ones that will be facing downwards. In this case, remember, we have got the supports, then we've got these loads. So we can have a normal, which is a concentrated like this. Then we can have a condition where we have got what? A distributed. So these are the types of loads that they are asking in this case. So that means in this case, we have got a concentrated. So we have got a concentrated loads or concentrated load. Then we have got the uniformly distributed load, which is our UDL. All right, so that is what we have. Question 2.2, a beam is supported at its end and is in equilibrium. It carries point loads of, okay, we're given the point loads, this and that. Sketch the diagram and indicate all forces acting on the beam. That's 2 marks for that. Okay, so let me just try to have the ruler here so that we can just try to sketch this together, guys, and see how our diagram was supposed to be like. All right, so let's just try to sketch this one aside here. Let's just hope it is going to be clear. So this is definitely beam. So we're just going to have our horizontal line in this case. All right, let me just try to shift this a little bit. All right, just a little bit, guys, so that we can see properly. All right, so the first part that we are given, we are supposed to understand each statement. That is, we are given that it's supported at its ends. There are supports at the ends. Okay, so meaning to say at the ends here, all right, this is question 2.21. Okay, that's 2.21. So we have got the end here. Let's say according to our diagram, this is our end point. So we are going to have a support here. It's supported, meaning to say there is a support. Okay, let me just try to carry my ruler a little bit up so that I can draw this properly. So I have a support here, and I also have a support here. All right, so this is what it means. So here I'm having a support. Here I'm also having a support. All right, let's check what is happening again. So we are given that if you are to check here so that we do not have confusion, I want us to work with this statement. The length of the beam is 14 meters, meaning to say from these 2 points that we have, there is a distance of 14 meters in between. Let me just indicate it here. I'll erase later on. But what we must know is that in between here, we have got 14 meters, okay? So now we are given that if this beam is in equilibrium, okay, it carries point loads of, take note, 5 kilonewton, 5 meters, and 3.6 kilonewton, 3 meters from the left end, which means these two forces, these two loads that we have, they are taken from the left. 5 kilometers, 3 meters, 5 meters from the left. So it's 5 kilonewton, 5 meters from the left side. Okay, so this is what we are going to have. We are going to have our 5 kilonewton. Let's just say at this point here, this is where I'm having my 5 kilonewton, which is 5 meters from from the left side. Okay, so this is what I have. This is the left side. So in between these points from the left side, I'm having 5 meters in between here. All right, so we can just indicate in between these 2 points here, I am having 5 meters. All right, and this is 5 kilonewton. All right, another part is 3.6, 3 meters from the left. So there is 3.6, which is 3 meters. So if this is 5, that means 3 meters is just before this 5. So there is another force here of 3.6, which is 3 meters. So maybe somewhere here, we are going to indicate another force here. All right, so that's another point load. So in this case, that is of 3.6 kilonewton and is 3 meters from the left side, which means from this side here, we have got 3 meters. So what does it mean? It means in between these 2 point loads, there is a distance of 2 meters, 5 minus 3, which is 2 meters in this case. All right, let's check the other part. Then and 6 kilonewton 4 meters from the right end. So there's 4 meters from the right. Okay, so from the right side here, this is our right side. So we've got 4 meters that we are going to take. But remember, this is 14. So 4 plus that, this 5 here plus the 4, it is going to give us 9, which means we haven't covered 9 meters. So there's a distance that is going to remain in between. That is what you're supposed to be very, very careful of. So you're going to cover 4 meters, then there's a distance in between. So let's say this is where we have our 6 kilonewton here. So we are going to have 6 kilonewton. We are given 4 meters from the right side. So which means from the right side here, I am having 4 meters. Okay, I'm done. On this part, let's check another part. Then we are given this part, we talked about it, that it is, the length is 14 meters. Okay, we talked about this. Then we are given that the uniformly distributed load between the 6 kilonewton and 5 kilonewton is 40 kg per meter. All right, between 6 and 5 kilonewton. Okay, let's check. Between 6 and 5, where do we have this point? This is where we have our 6, and this is where we have our 5. So in between these 2 points, there is a uniformly distributed load between these 2 points that we are given. That is what they are saying. And it's of 40 kg per meter. So this is given as 40 kg per meter. All right, so we're given in kgs per meter. So what is the distance between these 2 points? That is what we need to know. Remember, this is 5, this is 4. So 5 plus 4, that's 9. And 14 minus 9 is going to give us 5. So which means in between these 2 points of 6 and 5 and 6 and 5 kilonewton, there's a distance of 5 meters. So this uniformly distributed load is going to be affected for the 5 meters. So the diagram was just going to be like this. Okay, so this is for the diagram, guys. So we are going to use this diagram to answer any other question that follows. So we have to be very, very careful with that. All right, so the other part of the question now is calculate the reaction of the supports. Okay, calculate the reaction of the supports. Okay, so let's just name our points in this case so that we can calculate our reactions properly in this case. So we can adjust this point down, this point down, this point down. All right, so here I'm going to name this point A, B, C, D, and E. This is what I'm going to have. So that means the supports that I'm talking about, it's A and E. This is what you're going to have. These are the supports that we have. All right, so before we calculate this part, that is 2.22 in this case, before we calculate, let's focus on this distributed load that we are given, the uniformly distributed load that we are given, separated between 5 meters. We want to make this to be a point load just like the others here. So meaning to say, we must have the force in this case. All right, that's the force per meter. So take note here. We are given mass per meter. So we are supposed to have force per meter in this case. So the force per meter, it is going to be mass times the gravitational acceleration per meter. That is the mass of 40 kgs. So that's 40 times 9,8, whatever that you're going to have, it is going to be in newtons per meter. So what is going to be our force per meter in this case? So if you multiply properly, this is going to give us 392 Newton per meter. But these other forces, they are given as kilonewtons. So what are we going to do to express this in kilonewtons? We're going to divide by 1,000. That's 0.392 kilonewton per meter. So meaning to say here, we are given a distributed load of 0.392 kilonewton per meter. So how can we express now as a point load just like the other forces here? We just want to have this direct as a point load. So we are going to multiply this 0.392 per meter, which means by the distance of 5 meters. So 0.392 times 5. If we multiply this, we are now having it as a point load of 1.96 kilonewton. So this is going to be 1.96 kilonewton. Separated now between these 2 points, it was 5 meters. So 5 divided by 2, it is going to be 2.5 meters. So take note, guys, I'm answering the second question. So I'm using the first diagram. So do not confuse with this. The first question we are done on drawing the diagram. These adjustments, they are now for question 2.22. All right. So here we are going to remain also with 2.5 meters in between these 2 points. All right. So now we can calculate our reactions, guys, our support. All right, so I'm going to start with moments about point E in this case, which is this one. So moments about E. Taking moments about E. All right, so I'm going to take moments about point E. All right, so if you have to check in this case, A is moving this way back to E. This is clockwise direction. So meaning to say we are going to relate the sum of the clockwise moments equal to the sum of the anti-clockwise moments in this case. All right, so which other part do we have back to E? We can see that 6 moving back to E, that is this direction, that is anti-clockwise. 1.96 anti-clockwise, 5 kilonewton anti-clockwise again. If we check here, 3.6 anti-clockwise. So the rest are in the anti-clockwise. Okay, so you only have this one in the clockwise, which is A back to E. So that is A times the distance back to E, which is 14 meters, 4 times distance, which is equal to, we take all the rest, which is in the anti-clockwise. That's 6 back to E. We've got a distance of 4 meters. So that's 6 times 4. So this is going to be 6 multiplied by 4 plus, we move on to 1.96. 1.96 times the distance. This is 4 plus the distance here of 2.5. Remember, we said it's divided now for these 5 meters, 2.5 and 2.5. So 4 plus 2.5, that's 6.5. So it is going to be 1.96, which is our first times the distance of 6.5. Plus, we move on to another one. Here we've got 5 back to E, which means we are going to take this distance here. It's 5 meters plus 4 meters, which is 9. So it's 5 times 9. So this is going to be 5 multiplied by 9. Plus, we move on to the last one, 3.6 back to E. Remember, here we are at 9. So if we add this 9 and this 2, 9 plus 2, that's 11. So it's 3.6 times 11. So that's 3.6 times 11 in this case. We're going to combine, which is 14A is equal to, so if you are to combine everything properly on your calculator, you're going to obtain 121.34 in this case, which you can divide by 14 both sides now to obtain the exact value of A. So our A was going to give us 8.667142, which is 8.667 in kilonewton. All right. So we now have this force, or this point A in this case, which is 8.667 kilonewton. All right. So we are going to work now from A to have the answer for B, for E in this case. All right. So this time I'm going to take my moments about A so that we can calculate for E. Then you can test your answers to see if truly this is correct. All right. So we can see that this time, if we are to take moments about A, E is moving this way back to A. So E is moving in the anti-clockwise. And the rest of these forces, if you have to check, it's clockwise, clockwise, clockwise. They are in the clockwise. So you only have one in the anti-clockwise. So that is the advantage of this question. All right. So taking moments about A, taking moments about A in this case. So about A, we saw that E is moving in the anti-clockwise. So the sum of the anti-clockwise moments is going to be equal to the sum of the clockwise moments in this case. That is, E is the one in the anti-clockwise, this direction, it's anti-clockwise. So it's E times 14, which is the distance back to A. So that is E times 14, which is equal to the clockwise moments. We saw that all these, they are in the clockwise. So we are referring back to the point A. It's clockwise, 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 clockwise. So that's 3,6 times the distance between 3,6 and A, which is 3 meters. So 3,6 times 3. So you're going to multiply. In this case, this is going to be 3,6 times 3 plus we move on to another one in this case, which is 5 back to A. So there's a distance of 5 meters. So that's 5 times 5 in this case. So we are going to have 5 times 5 plus we move on to another one in this case, which is the 1,96 as a point load now. So that's 1,96 times the distance between. So if you have to take, we've got 5 meters and the 2,5 meters. So if we add 5 plus 2,5 back to A, that is going to be 7,5. All right, so this is going to be 7,5 in this case. All right, so we are going to have 1,96 times 7,5. Okay, plus we still have another force in this case, which is 6. So 6 here, back to the point A, we see that we have got 5 meters here. So this is 5 and another 5. So 5 plus 5, that is going to give us a 10. So that's 6 times 10. The distance is 10 meters. So 6 times 10. All right, so like this, we can calculate the value of E if we combine everything. So E times 14, that's 14E is equal to everything. On this other side, we are going to obtain 110,5. So if we divide by 14, both sides to find the exact value of E, we are going to see that our E is going to be 7,89285 and so on, which is 7,893 if you round off to 3 decimal places. Okay. So that's it, guys. We can even check to prove from our Newton's third law to say that the sum of the upward forces must be equal to the sum of the downward forces. So the upward forces, we've got the point A and the point E. Remember that we calculated our E in this case, we got 7,893. So if you are to add these two, A plus E, we are going to obtain 15,56, which is the same answer that you must obtain if you add 3,6 plus 5 plus 1,96 plus 6. You're going to also obtain 16,56. Okay, so that was the question. Guys, for this one, I think everything is clear. Now on the other part of the deck of the question, on question 2.23, we are now given to draw a shear force diagram for this information, the shear force diagram. Okay, so I'm just going to relate back to the normal diagram that we had previously, this one, so that we can have our shear force diagram. Okay, so let me just erase. Okay, sorry, let me erase this part here so that we can just use we can just draw our shear force diagram down here so that we can understand what is happening here, what is actually happening. All right, so from your shear force diagram, remember we are going to take this from a horizontal line. So I'm just going to extend my points in with a horizontal line in this case. All right, so let me just extend my points here. All right, so sorry for that. It's gonna take us some time because I'm using these instruments here, guys. But the idea is still the same, guys. All right, so you're supposed to use a suitable scale that you're going to work with. But in this case, guys, if you have to check what I'm using here, it's gonna take us a lot of time. So I'm not going to apply that condition, but I'm just going to show you the suitable points that you're supposed to have. All right, so let's extend this one from A. We extend from B. All right. We also extend from C. These are the important points on your diagram, okay? So you just extend those points. We extend at, okay, at D, A, B, C, D. We move on to D, okay? So we extend this one at D, major points. You work with the major points, all right? You extend this one at E, at major points, all right? So that is what you're going to have. If we are to check the first condition is happening at 0, we are starting direct at this point at 0. So this is 2.23, the shear force diagram, 2.23, our shear force diagram in this case. So you're starting direct at 0 kilonewton in this case, that is at this point, at this. Okay, but at this point that we are given, we can see that we have got a support direct at point A. There's a support of 8.667. So what are we going to do with this support? We are going to add, because it's a support is going up. All right, so we add this one. So at 0, we are going to add 8.667. So if you add 8.667, you're going to remain at 8.6667. Okay, so that is what you're going to have in this case. We are saying that's a 0 plus 8.667 in this case, which is going to be 8.667. So it's a point, it's a support, it goes direct. Okay, so it is going to be, let's say this is where I'm having my 8 comma. So you're supposed to do this according to scale, but like I said, here I'm just going to show you the major points that we are supposed to have on your diagram. Okay, so let's say this is where I have my point 8.667. So I'm going to write 8.667 kilonewton at this point. Okay, so let's see what is happening from A to B. Okay, from A to B, we have got nothing. There is just a free distance that you are moving of 3 meters. So you're just going to move 3 meters like that. There is nothing that is being affected there. All right, so I'm just going to move direct from this point up to B. Nothing is occurring. So which means I am still at 8.667 in this case, because we never subtracted or added anything. All right, now at point B, this is where we are now. We are at 8.667. This is where we are at point B. We are going to see that there is a point load at point B in this case of 3.6 kilonewton. A point load is facing down, so we subtract. So at 8.667, we are going to subtract 3.6. So this is where we were, guys. We were at 8.667. So we subtract 8.667 minus 3.6, which is a point load. We are going to obtain 5.067. So a point load, it goes down straight to that point. So you're going straight. So let's assume according to your scale that you are having, you are going to have your 5.66 at this point. So you're going to join direct to that point. All right. So here we are going to join direct to the point that you are saying that's your 5.067 at this point here. All right. So that's what I'm going to have in this case. All right. So here I'm going to write the points according to the way that I'm given. So that's 5, we said this is 5.067. Okay, so that's 5.067 kilonewton at this point. Okay, that's at B. Between B and C, what is happening between B and C? Okay, there is nothing, just a free distance of 2 meters. So we're going to move again the same way that we did before. So this one is going to be a horizontal line. So there's nothing that we have changed. It is moving straight to the point at C. So we are going to move straight to the point C, meaning to say we are still at the point of 5.067 at this point. All right. Then what is happening at C? At C, we have got 5 kilonewton in this case, a point load again, which is facing down. So we're going to subtract. So what are we subtracting? 5. From where? From where we are at this point of 5,067. So if we are to subtract 5 at 5,067 minus 5, we are going to remain at 0,067. So 0,067 is just a little bit below this line, not below, just above, just a little bit above the line. So maybe approximately at this point here. So we are going to join to that point. Okay, so that means this is going to be like this. We join straight. It's a point load. So you join straight to that point. All right, straight to the point. That's at 0, that's 0, 067 kilonewton. All right, that's at this point C. Between C and D, what is happening between C and D? Between C and D, we have got a uniformly distributed load, UDL, between these points, this one and this one, which was 0,392 kilonewton per meter, and we multiplied and got 1,96. Between these 5 meters, we got 1,96. So we are going to subtract 1,96 direct from this one. So 0,067 minus 1,96. It is going to give us a negative 1,893, which is in the negative region below this line, and it's a UDL, which is going to be a slanted line like this. So it is going to slant up to negative 1,89. So approximately, according to your scale, assuming here it is going to be at this point, D, maybe we are having this at this point. That means we are going to join to that point of negative 1,893 kilonewton from this point. So it is going to be a slanted line like this, all right? So we are going to join these 2 points from this point up to this point here. All right, so this is how you represent your uniformly distributed load like this. All right, so that is what we got in this case. I hope everything is clear in this case. All right, let's check what is happening now between the point D and E, because we are now at point D. All right, so between point D, in fact, at that direct point D, after there is a point load of 6 kilonewton facing down, so you're supposed to subtract again. At that point where we are, we subtract 6. So we are at the point of negative 1,893. We subtract 6, so that is going to be negative 7,893, which is in the negative region. But this one is going direct straight because the point load, so it goes straight. So straight, maybe at this point, that's where you have your negative 7,893 kilonewton. So this one, like I said, it's a point load. So you join straight, direct, straight down to this point. All right, so this is where we are, guys, at negative 7,93 kilonewton. All right, that's at point D. Between point D and point E, this is what we have. Between point D and point E, there's nothing at all, just a free movement. So you're going to move 4 meters between D to E. Okay, so this is just going to be a horizontal line between this point. All right, so here we are just going to move straight up to the point at E. All right, so straight up to this point with the same measurement or the same value. That is the one that is at this point at negative 7,893. This is where we are. And if you are to check at point E, there is a support, which is a support. It's a positive. It's facing up. So we're going to add 7,893. But by adding 7,893 to minus 7,893, this is going to give us a 0. So which means we are going back to the original point at 0 kilonewton, which means that's to show that truly this is in equilibrium, it is going to give us a closed figure. So here, remember, it's a support, so it is going to be straight vertical line going up. So it is going to go up to 0 like that, and it gives us a closed figure in this case. All right, so this was how our shear force diagram was going to look like. These are the major points that you were supposed to have on your shear force diagram. So I hope we had these points from 0 to 8,667 up to the point where we get back to 0 kilonewton again. All right, so that was our question 2.23, which is to mark the last question on question 2 on moments. That was it, guys. Having a total here, it was having a total of 12 marks. Okay, let's check what we have on question 3, which is on forces. Okay, so this one, it is on forces. Okay, let's just try to remove some of the other things here. So we are given the first part of the question to give one difference and one similarity between an equilibrium and a resultant. All right, we are talking about an equilibrium in this case and a resultant. What is it that we have that is similar, and what is it that we have that is the difference? That we've got the difference and the similar in this case. Okay, so the major thing is that they have the same magnitude, these two. Okay, so they have the same magnitude. Okay, so they have the same magnitude, all right, but are in different direction or opposite direction, but are in opposite direction, in opposite. So the opposite now direction, meaning to say that's where we have the differences now. So this is opposite direction like that. All right, so that's 3.1, just 2 marks for that if we are to check. Okay, then 3.2, we are now given forces which are acting at a point, which is this point here. Then calculate the magnitude and direction of the resultant force. The resultant force of the forces acting at a point, that's 7 marks. Okay, so if we are to check, guys, on our information, the diagram, the only thing that we can just take into consideration here is the 110 Newton. Take note, I told you guys that the forces must be from a point, not to the point like this. It's facing into the point. So you extend that one down. It must be from the point. Okay, so from the point, it must continue downwards like this. So this is where we are going to end up with our 100 Newton in this case. Okay, and the other thing, the forces must have angles between the force and the horizontal line. The force and the horizontal line, like this one, 120 Newton, we are given the angle of 30 degrees between these, which is fine. So this one, we're going to use it. But if you check 60 Newton, we do not have the angle between this force and the horizontal line. We do not have. So we're supposed to calculate that angle. Okay, so how can we have this angle? If you are to check, this is 30, this is 120. So if we add these two from 180, we are going to have 180 degrees minus 30 plus 120, which is 150. So if we subtract, that's 30 degrees, meaning to say there is an angle of 30 degrees between 60 Newton and the horizontal line. So this is the most important part that you're supposed to have. With this information, we can calculate the resultant. How? We are going to need the total for the horizontal. All right, so we are going to take the horizontal, the vertical, as I'm just going to calculate on this space here. All right, so remember that the horizontal components are the ones that work with cos of theta. So that means this cannot be a horizontal, it's a straight vertical. So there's nothing on this 100, okay? So we are going to relate 60 back to the horizontal. Here, this is the horizontal, it's on the positive, okay? We know that, guys, from the point here, the horizontal is affected to the right, to the left. To the right, it's a positive. To the left, it's a negative. So 60 is to the right. So this is going to be equivalent to 60 cos 30 degrees. Horizontal components, they use cos theta. So that's 60 cos. And if you check on the left side, we have got 80 Newton, which is a straight horizontal. It's a straight horizontal. There's no adjustment that we can do there. So that's minus 80. Then we have got 120 between an angle of 30 degrees. So it is going to be minus 120 cos 30 degrees. It's in the negative region. That's why we are writing as negative 120. So if you simplify everything, this is going to give us negative 131,9165 and so on. So this is going to be 962 Newton in this case. So we've got the horizontal components. We move on to the vertical components, which takes sine. So they are going to use sine theta. So for the vertical components, anything above, it's a positive. Anything below, it's a negative. So here we are in the negative region. So that's negative 60 sine 30 degrees. It is going to be negative 60 sine 30 degrees. 100 is in the negative. So it's a straight vertical, this one. So it's negative 100. 120 is also in the negative side. So it's negative 120 sine of 30 degrees. Then there is no way 80 can be a vertical. It's a straight horizontal, that one. So there's no way that we can make this to be a vertical. So I want you to combine. If you combine everything, you are going to obtain negative 190 Newton. So how can we have the resultant force from this? Okay, I actually encourage you to represent this in form of a diagram so that you can actually understand what is happening. The horizontal, it's a negative, meaning to say this is being taken to the west. Remember, if it is a negative horizontal, that's to the west. The vertical, it's a negative, which means it's going down. This is what? This is to the south. So the resultant diagram, we shall have our horizontal on the left side, which is to the west, then the vertical down, which is on the south side like this. So this is how your diagram is going to look like. The horizontal, this is the horizontal component. This is your vertical. So our horizontal, it's negative, vertical also negative. So it can only be in this quadrant. Okay, so this is your horizontal component in this case. This is your vertical component in this case. All right, so this is going to be your resultant, and also we can have our resultant angle in this case. All right, so that is what we have in this case. So let us calculate and see what we have. The resultant from the vertical and horizontal, we understand that the resultant is going to be the square root of the horizontal component squared plus the vertical component squared, or you can write this as fx plus fy squared, whereby our resultant is going to be the square root of our horizontal. That's negative 131,962 squared, plus the vertical component, we got a negative 190 Newton. So that's negative 190 Newton squared. So you're going to have your R in this case as the resultant of 231,33086, which you round off is going to be 231,331 Newton. All right, so that's our resultant. Then we can calculate our angle, which is theta in this case, which is the angle between these 2 points, between the horizontal and the resultant. So this is your theta. So our theta is taken from arctan of opposite over the adjacent. So the opposite is the vertical component and the adjacent is the horizontal component in this case. So that means theta is equal to arctan. The vertical component, remember your vertical is negative 190. So that's negative 190 over the horizontal, which was negative 131,962. So that is going to give us theta in this case, which is 55,2185 and so on. So if you round off it to 3 decimal places, it is going to be 55,219 degrees. All right. So therefore, our resultant in this case taken from R, which is 231,331 Newton. But the angle that we have in this case, if you are to check here, we can take this angle here in between from the side of the west. This is your west side, this is the west, and this is the south. So it's west theta to the south direction. So this is going to be west 55,219 degrees to the south. Take note, guys, it is from the west to the south. Okay, so that is what you're going to have on our resultant in this case. So that was question the first part of our question 3, which is 3.2, having actually total of 7 marks in this case. All right, so let's check the other part of the question in this case and see what we were given. So on 3.3, we are now given that all right, so there's no information, it's just calculate the value of P that you're given. Okay, so here we want to calculate the value of P. So we understand that we can take these as forces we can take these forces up and forces down, because we've got these forces which are going up, these forces which are going down. So you can take that as an advantage to calculate the value of P in this case. So that's 3.31. The sum of upward forces from our Newton's third law is equal to the sum of the downward forces. That means P plus 45, which is the upward force, is supposed to be equal to the downward force 65 plus 55 in this case. So P plus 45 is equivalent to the sum of the two, which is 120. So if we subtract 120 minus 45, this is going to give us 75 kilonewton. So we have our P here, which is 75 kilonewton in this case. All right, so let's check the other part of the question. All right, let's check the other part here. 3.22. Calculate the magnitude and the nature of RS and WS. Okay, so we have got RS here and this WS in this case. All right, if you are to consider from the 60 degrees that we are given here on point, or on this point P, that is where we are going to focus on. All right, so we need SR and WS. Okay, so if we are to consider this, we are going to see that there are upward forces here. Okay, let me do this way. 3.32 from the P that we have, it's a force that is going up. So we can say that the sum of the upward forces is equal to the sum of the downward forces, but referring to P and RS to say that P is going up, which is 75 kilonewton, is equal to RS now is affected by an angle of 60 degrees. So this is going to be RS sine of 60 degrees, because it's a vertical component up. It's a vertical component. So that's why we are using sine 60 degrees. Okay, so to find RS, we can simply divide by sine 60. Since we are multiplying, we can divide both sides by sine 60. So that means we are having RS, which is 75 divided by sine 60. So it's going to be 86,602 and so on, which is 86,60254. So that's 603 kilonewton in this case. All right, so that's for RS. Then for WS, okay, also the nature. Okay, so here we are representing, we talk about a strut in this case. Then for WS in this case, if you have to check, it's part of a horizontal component. So you can deal with the horizontal components to say WS, we can refer to the forces on the right side being equal to the forces which are on the left side. So meaning to say on the right side, that's where we have our WS. It's on this side. It's on the right side than RS. RS is on the left. So meaning to say WS in this case is equivalent to the product of RS and cos, because we want to make this a horizontal. So it is going to be RS cos now of 60 degrees. So that is what you're going to have at the end. So we can calculate WS, since RS, we calculated it before. That's 86,603 times the cos of 60 degrees. So that means our WS in this case is going to give us 43.03 and so 15 and so on. So if we round off to 3 decimal places, that's 43.302 kilonewton, which is a tie in this case. All right, so that was our WS. the magnitude of RS, the magnitude of WS in this case, 15 marks on this question. Question 4, give 2 advantages, that is on friction, advantages and disadvantages of friction in this case. All right, so we are given to have these as the advantages and the disadvantages. Okay, so we are going to, okay, let me just have it here. All right, so as for the advantages, all right, so this is question 4.1. So what are the advantages, guys, that we have if we are dealing with friction in this case? So we know that friction, it can prevent slip between 2 contacts. Okay, so it can prevent slip between 2 contact surfaces, between 2 contact surfaces. All right, so that's what we have in this case. Also, it removes material. Okay, so that's another part. Also, it brings movement to standstill. Okay, it can bring movement to stand still. That is to a halt or to a stationary, to a standstill where there is no movement. Okay, so there are so many, guys. So I want you to list others and so on. What are the disadvantages? So it causes noise. There is a lot. It causes noise. In this case, there can be issue of noise. It causes drills to become blunt. Okay, so it also causes things like drills or blades. All right, things like this to become blunt. Okay, to become blunt in this case. Also causes wear and tear. Okay, so it also causes wear and tear. So there are so many. So I want you to list down on the comment section if you've got any other advantages that can help someone. List them on the comment section. It can actually help us a lot. All right, on 4.2, we were given Fig 4 shows a body with a weight of 492 Newton being pulled along a horizontal plane at a uniform velocity of 5 meters per second by a force Q. So there's a force Q here that is moving this side, inclined at an angle of alpha to the horizontal. The coefficient of friction between the body and the plane being 0.32. The power transmitted to the body is 0.62 kilowatts. All right, so this is what we have. We have got the weight in this case, the weight of 492 Newton put along the horizontal. We also have the velocity of 5 meters per second at an angle of alpha. The coefficient of friction, we are also given as 0.32. Also, we are given the power of 0.62 kilowatts, which you can convert to what by multiplying by 1,000. This is 620 watts. So that's your power in this case. Okay, so the question is to calculate the mass of the body, the mass of the body on question 4.21. Okay, so we can actually calculate the mass because we are given the weight of the body in this case, a body with a weight of. So we know that weight is equivalent to mg. So to calculate mass, can divide by g both sides. That means our mass is going to be weight over the gravitational acceleration. So the weight is of 492 divided by 9.8, depending with the units, the value that you're given on your formula sheet. So if you divide 492 divided by 9.8, you're going to have 50,202,048 and so on. So it is going to be 50,204 kgs. So this is your mass in kgs. 4.22, the magnitude of the friction force, the magnitude of the friction force. Where can we have friction force? We have got power and we have got velocity. Remember that power is a product of, okay, let's write this, 4.22. Remember that power is a product of the frictional force times the velocity. So the question is for us to calculate the magnitude of the frictional force. This frictional force is the horizontal component. In this case, it represents the horizontal component, which is F cos alpha. Is in actual sense, it's P cos alpha. Is it P or Q? Okay, this is Q, not F. So it's Q cos alpha from here, the horizontal component in this case from this Q and alpha. We've got horizontal and the vertical. All right, we've got our horizontal, we've got our vertical. All right. So the horizontal component is the one that we are as the frictional force, which is going to be divide by V both sides, so that we can calculate this because we have got power and we also have velocity. So our frictional force is going to be power over velocity, which is the power of 620 watts or 0.62 times 10 to the power of 3. Everything over the velocity of 5 meters per second. So we are going to have our frictional force. So the frictional force, when calculated from your calculator, you are supposed to obtain something like 1,002, so not 1,000, but 124, just 124 Newton. All right. So that's our frictional force. 2 marks for that. All right. So let's check the other part of the question that we are given, which is now on question 4.23. The normal reaction between the body and the plane, the normal reaction. Okay, we know that the normal reaction can be actually taken. This is 4.22, 4.23. Okay, or 4.23. We have got, in this case, remember, we have got the coefficient of friction. We also have the frictional force. So we know that the frictional force over the normal reaction, we can obtain our normal reaction in this case. So that means we can calculate, we can just substitute our values in this case. If you saw that our coefficient of friction, it was 0.32 here, 0.32. So we are going to multiply 0.32 to the frictional force. We have got frictional force of 124 in this case, all right? So that's 0.32 is equivalent to 124 over the normal reaction. So you can calculate NR by cross multiplying. This side is going to be 0.32 times NR, which is 124, divide by 0.32, both sides, divide by 0.32, both sides. We have our normal reaction in this case, which is going to be 385. So it is going to be 387.5, sorry, 387.5 in this case, like that. All right. So that's your normal reaction in this case. Okay. Then the other part of the question is to calculate the vertical component of force P. Okay. If you checked previously, I indicated here that this is where we're going to have our vertical component in this case. So this vertical component is just an opposite part to say we are going to have our normal reaction like this, the vertical component. So we are just going to have the difference between these two in this case, all right? So we, sorry, I'm now confusing you guys. In this case, we are given the vertical components. Let's get back to the question. The vertical component of force what? Of force Q in this case. All right. So the vertical component of force Q is opposed by the weight on Q. Remember, the weight is actually going, it is opposing. Remember, if you're given weight due to gravity, it will be tending to be going down. Our vertical component going up in this case. So the difference between these two, it is going to give us our vertical component in this case. So which means our vertical component is going to be equivalent to the weight minus the normal reaction in this case. We're going to subtract the normal reaction that we calculated because it's going up. So our weight was 492 minus the normal reaction. Well, normal reaction, it was 387.5, the one that we just calculated here. This one, 387.5. So you subtract these two, all right? So if we subtract these two, we are going to have 104.5 Newton. All right, so that is your vertical component. So the question can even further on to ask you to calculate the value of Q. If you were asked to calculate the value of Q, you find the resultant. Q is going to be the resultant of, that is the horizontal component squared plus the vertical component squared. So you're going to square this, whereby your vertical component is the frictional force. So that is how you can calculate Q. But we are not asked to calculate Q. The question is for you to calculate the vertical component of Q. All right. So that was our question 4. Then question 5, which is on heat. So we are given a question on heat in this case. So the first part of the question was to list 3 factors to determine the amount of heat energy absorbed or given off by a substance. What are these factors? So in order for you to know these factors, you must be able to know the formula for determining this amount of heat, which is Q, where Q is equal to MC times the change in T, whereby this C is our specific heat capacity. All right, so which means these are the 3 factors that we have here. We are talking about the mass of the object, all right? So we are talking about the mass of the object in this case, which is supposed to be what? Which is supposed to be in kgs. The specific heat capacity, it is telling us about the type of what? Of material that you are using. What is the type of material that you are using? Then the change in T is for the temperature, that it can be a rise or it can be a fall in temperature. So this is the rise or fall in temperature, or change in what? Or change in temperature. So these are the factors which determine the amount of heat. All right, 5.2, we are given that 500 liters of water is heated from 300 kelvins to 370 Kelvin in this case. Okay, the heat capacity and so on and so on. All right, so this is the information. Okay, let's just take our information down in this case. I just hope if I take it, it's going to be fine. So we are given that it's heated from, that is our temperature in kelvins in this case. So we've got T1 in kelvins, which is 300 Kelvin, and T2, which is 370 Kelvin in this case, with a heat capacity of, so we are given the heat capacity in this case, or which is the of coal, which is the heat value in this case. Okay, that's the heat value of coal, which is 30,000. So that's 30,000 kilojoules per kg. All right, remember this is mostly given in megajoules, whereby megajoules is times 10 to the power of 6. So if we take these 3 zeros, it is going to be 30 megajoules. That is 30 times 10 to the power of minus 6. That is 30 megajoules per watt per kg in this case. All right. Then we are given the quantity, the specific heat capacity in this case of water. So we have got the specific heat capacity of water. So in this case, I'm just going to write it as sea water like this, of 4,187 kilojoules per kg Kelvin, Okay. So the question on 5.21 was to calculate the rise in temperature of water in degrees Celsius. So you see that these values that we have in this case, they are in kelvins. But remember that for you to convert to kelvins, what actually happened is that you were adding 273. So you're going to subtract 273, but it does not affect anything at all. So your change in temperature is just going to be equivalent to T2 minus T1, that is 370 minus, in this case, 300. So this is going to give us 70 degrees Celsius, because the answer is given in what? In degrees Celsius in this case. Okay, so like I said, you can first convert this to degrees Celsius. You convert this to degrees, still you're going to obtain the same answer. It's a waste of time, that one. Okay, but still it's fine because if you've got information that you can use to obtain an answer, then it's okay. 5.22, the quantity of heat required in megajoules. Okay, so we are now back to Q, which is the quantity of what? The quantity of heat. And we say this quantity of heat is given by mass times the specific heat capacity. So we are going to use this as 5.22, which is Q is equivalent to mass times the specific heat capacity times the change in this case of temperature. So in this case, this is the specific heat capacity for what? For water. So that means our Q is going to be the mass. All right. On our information here, we are given not the mass, but the volume. Okay. It's here, 500 liters of water, 500 liters, which means we are given volume. So from this volume, how can we end up with the mass? How can we relate liters with mass? How is this two related? Okay, what we must know is that a kg is equivalent to 1 liter. So if it is 500 liters, it's 500 kgs. So which means we are given a mass of 500 kgs in this case. All right. So that's it. Our mass is 500 kgs. So we are going to have 500 times the specific heat capacity of water, which is in this case, it was 4,187. So take note, this was in kilojoules. So your answer is going to be having kilo at the end, all right? Times the change in temperature of 70. So we are going to have our Q. If we multiply, this is going to give us 146545. That, remember, I said if you multiply with this kilo, your answer is going to be in kilojoules. All right, so let's check. Also, the units we are asked this in megajoules. So you're supposed to change this to megajoules. So kilo, that's times 10 to the power of 3. So we need another kilo here. So our answer is going to be 146,545. If we divide by 1,000, that's times 10 to the power of 3 times 10 to the power of 3, this one that we are given here, which is kilo. So times 10 to the power of 3 times 10 to the power of 3, it gives us 10 to the power of 6. That means we now have megajoules. So our Q is going to be 146,545 megajoules in this case. All right, so that was the value for Q. All right, let's check the other part, the quantity of coal required, which means the amount of coal that is required. So remember, we are given the heat value for coal, and we also have the energy that was being used. So we can calculate the mass from there. All right, so that's 5.23 in this case. We can even use it on this one. We can even calculate on this side. All right, so 5.23. Remember that mass is equivalent to energy. Mass is equivalent to the energy, which is the Q over the heat value. So this is what we have in this case. So we are going to divide. So we are going to have our mass. So take note, because of the units, you can, if you use in kilojoules, you use your heat value in kilojoules. All right. If you use megajoules, like here we are asked to convert our answer to megajoules, we are going to use this as 146,545, which is in megajoules, divided to the heat value, which means we are supposed to use heat value in megajoules, which is 30 megajoules per kg. So if we divide by 30 megajoules per kg, that means we are going to have our mass in kgs. 1 divided by per kg, that gives us a kg. Megajoules and megajoules cancels. So this is going to be 4,885. Okay, 4,884,833. So the 8 is going to change 4 into 5. So that is the quantity of heat which was required, which is 4,885 kgs. All right, so that was our question 5. The question of 5.2, 5.21, 5.22, and 5.23. On 5.3, we are now given a square plate with sides of 1,24. All right, let's just try to remove so that we can even try to work it aside here. So here we are given that there is a square plate in this case that we are given that is, sorry for that. So let me just try to bring this one back. So we are given that this square plate that we are given, it's of size 1,24 meters long and heated from T1, 20 degrees Celsius to T2, which is 124 degrees Celsius, and also the coefficient of area of expansion in this case, which is 36,5 times 10 to the power of -6 and so forth. Calculate the final area All right, so that's 5.3 in this case. So if you had to check in this case, we have got an area, we have got a square that we are given, and this square, we know that if you are dealing with a square, all the sides are the same. So this square is of side 1,24 meters, 1,24 meters. So we are given that it was heated from 28 to 124. So 28, it's our initial temperature in this case, and the final temperature is the 124 degrees Celsius, having the area of the question of area of expansion, not linear, but it's area expansion, which is 36,5. So this is our beta, which is for area. So that's 36,5 times 10 to the power of -6 per degree Celsius, which is equivalent to 2 alpha, which is for the linear. So the question is, we are supposed to calculate the final area in this case. So how are we going to have our final area? We know that the final area is supposed to be the original area plus the change in this area that we are given in this case. So we have got the final area being the original area plus the change in area. So we have the original area because here it's a square. We can just simply have our original area, which is side times side, or just side squared. So this is side times side, where you multiply 1,24 and 1,24. But what about the change in area in this case, which means we're supposed to calculate this first. So the change in area, remember that is given, if you are given beta for area, therefore it is going to be beta times the original area, in this case, times the change in temperature, which is T2 minus T1. So that's T2 minus T1. This is the original area, which is side times side for a square. So we can calculate the change in area. So we have got our beta, it was 36. This is 36, take note. So we've got 36,5 times 10 to the power of -6 times the original area, that's side times side, 1,24 times 1,24, or simply 1,24 squared, times the change in temperature T2 minus T1. Our T2 is 124. So that's 124 minus 28. So this is going to give us the change in area in this case. So our change in area, simplified properly, it is going to give us 0, so that's 0,00538 and so on. So we can even write this to milli units, 1, 2, 3, that's 5,387 times 10 to the power of -3 in square meters, like that. Okay, so that is our change in area, not the final. The final is the original area plus the change in area. So therefore, we can calculate our final area in this case. So therefore, our final area, we said, is the original area, which is side times side here, our original area here, which is 1,24 times 1,24, the area of a square, plus the change in area, the one that we calculated now, of 5,387 times 10 to the power of -3. So this will give us the final area for this shape, which is a square. So if you are to simplify this properly, we are going to obtain 1,542,988 and so on, which is going to be 1,543 square meters if you round off to 3 decimal places. So this is going to be your final area in this case. All right. So that was the typical question. Very, very interesting type of a question, because here you see the beta part here, this beta, the coefficient of area, it's not the linear, it's for area. So you're supposed to be very, very careful. So that was a question on question 5 on heat, carrying a total of 13 marks. So this was actually 13 marks. All right, on question 6, that is hydraulics, we are given to write down the equation in terms of air pressure with reference to gauge pressure and absolute pressure. All right, so remember that absolute pressure is the sum of air pressure and gauge pressure. So that means we can make air pressure the subject. So air pressure is going to be the difference now of what? Of the absolute pressure. So it is going to be absolute pressure minus the gauge pressure in this case. So it is going to be minus the gauge pressure. So that's 2 marks for that. All right, 6.2, we are given that Patrice Mashoniani, an engineer. Okay, that is Masholeane. Okay, Masholeane. Okay, so we've got Patrice here, an engineer, was given the job to check a water pump with a piston diameter 12 centimeters that delivers 0.025 245 cubic meters per stroke. All right, so this is the information, guys. Let's just try to take it down. So what is happening is that Patrice here is going to check, okay, the job. Then we saw that there's a diameter, so we are given here the diameter, or we can even just try to write it on a little bit on top here. So we have got a diameter of 12 centimeters, which we can convert to meters. 1 meter is 100 centimeters, so you can divide by 100, which is 0.12 in meters. Then the volume that it delivers, it's 0.0245 cubic meters per stroke. That is per each stroke. The average force on the piston per working stroke, also we are given the average force of 6,300 Newton per working stroke in this case. All right, so the question is, on question 6.21, to calculate the pressure of the fluid during the working stroke, on these working strokes that you are given, what is going to be the pressure? All right, so 6.21, our pressure. We know that actually pressure can be taken from here, from rho GH, or we can take pressure from force over area. So we do not have density, we have GF, we do not have this size, so which means this part is not going to work. So meaning we are left with force over area. We have the force, we do not have area, we have the diameter. So we can calculate this to say it is going to be force over, remember that area is pi d squared over 4. So this is going to give us the exact pressure that we want in this case. All right, so our P for pressure is going to be the force. So we can substitute our force in this case is 6,300. So this is going to be 6,300 over the area, which is pi d squared. Make sure that your d is diameter in meters, which is 0.12 squared, everything over 4 like this. So we can simplify this to give us the exact amount of pressure that is required. So our pressure is going to be 5, we are going to have 557,042,3 0.3008, yes, 0.3008 like that in pascals. So you can convert to kilopascals in this case by dividing by 1,000. Remember, kilo is times 10 to the power of 3, so you multiply by the vice versa. So it is going to be 557,042 in kilo pascals. You divide by the opposite, kilo, 1,000. So you divide by 1,000. All right. So in this case, 6.22, the length of the stroke in millimeters. So we are asked to calculate the length of the stroke, which is, we are talking about what? About h in millimeters. Take note, from the information we have got here, the volume per stroke, which means there's something that we can talk about here from this volume. All right, we understand that the volume can be taken from area and the height, which is the stroke length. So we can say that since these two can be combined to say volume is equivalent to area times the stroke length, which is the height. Therefore, we can calculate this h here, which is the height, which is our stroke length, by dividing by the area outside, because we have the volume. So our h is going to be volume over area. So the volume is given in this case as 0.00245, that one that you're given. So this is going to be 0.00245 over the area. which is the same area that we calculated from pi d squared. So it was pi times 0.12 squared from this one, everything over 4. We have this value here. So everything here is going to give us h. So our h is going to give us 0.21667 and so on and so on in meters. But take note, your answer is needed in millimeters, which means we multiply by 1,000. Since 1 meter is equal to 1,000 millimeters, so if you multiply by 1,000, this is going to be 216,627 and so on. So the number there was going to round off this to 8, which is now in millimeters. So that is our h, which is our stroke length. So that was the tricky part of this question, but it's not that tricky. It's not that tricky. Okay, then on question 6.23, the work done in 25 strokes, take note, in 25 strokes in megajoules. We know that the work done is supposed to be taken from the pressure that we are given, all right? Let's just write our formula here. Our formula was supposed to be work done is equivalent to pressure times the volume, just like this. But because we are given the volume per stroke, so we are going to multiply by the number of pumping strokes. I mean, the number of strokes that we are given in this case, which is 25. So everything here, we have our work done, pressure. We have got our pressure here of 557,042 kilopascal. So kilo, that's times 10 to the power of 3 times the volume per stroke. So take note, this is the volume per stroke of 0.00, this one 0.00245, okay? So we're going to multiply by the volume per stroke, then times the number of strokes. So it's 0.00245 times the number of strokes, which is 25. That is going to give us the exact answer for our work done in this case, which is going to be, our work done is going to be, that is 118.8225 joules, like that, okay? So this is what you're going to have. But here, according to the instruction, we are given that this work done is supposed to be in megajoules. So mega, that's times 10 to the power of 6. So for you to convert this, you multiply by the inverse of 10 to the power of 6, which means you multiply by 10 to the power of minus 6. We are going to have our work done as 0.0341 in megajoules if you multiply by 10 to the power of minus 6. The answer that you get, you round off to 3 decimal place, you have it in megajoules, like that. All right. So that was question 6.23, marking actually the last part on hydraulics of this question. So that's what we had. Let's check the other part of the question, which is question 7, where we are given electricity. On electricity, the first part was to define the term ampere. Okay, that's the ampere. So ampere can be defined as follows. Okay, so let me show you from this screen here that the ampere is that constant current which is maintained in two straight parallel conductors of infinity length, of negligible cross section, and placed apart in a vacuum, would produce between these conductors a force equal to 2 times 10 to the power of minus 7 Newton per meter of length. So that is how you define an ampere if you're asked to define an ampere, guys. All right. Let's get back to the question. We are given in this case 3 cells, each with an EMF of 3 volts and internal resistance of 0.5 ohms are connected in series with an external circuit as shown. Okay, so they are in series in this case, and each, take note, each cell, there are 3 of them, is having 3 volts. So which means our EMF, which is E in this case, is going to be 3 times 3, which is 9 volts. So here we are going to have 9 volts. Then the internal is, there are 3, they are in series, which means we are going to add 0.5 plus 0.5 plus 0.5 3 times. That simply means we are multiplying 0.5 times 3 for the total internal resistance, which is going to give us 1,5 ohms. So here we have got 1,5 ohms on this total internal resistance. All right. So let's check now what the question is all about. The first question that we are given is to calculate the equivalent resistance of the circuit. All right. So according to this circuit, we can see that we have got 3 resistors in parallel after everything is in series. So which means we can work with the parallel combination in this case to calculate the total resistance for the parallel resistor. So how are we going to have our RP? In parallel, there are more than 2, so you can use the formula 1 over RP is equal to 1 over the resistors. So it's going to be 1 over 6 plus 1 over 3 plus 1 over 9. You add 1 over the resistors that are in parallel. So 1 over RP is going to be, if we add these resistors, we are going to obtain 11 over 18 in this case. So to simplify RP, just interchange, divide by 1 divide by this, we are going to have RP. So RP is equal to also 1 divide by this, we are going to have 18 over 11, which is as a decimal, it is going to be 1,636 like that, which is 636 ohms. So this is for the parallel combination of these 3 resistors that we have. They are in parallel. So we have calculated the total for these 3 resistors. So after combining this, it means now we have a single resistor here that is going to be connected to this resistor, to also the resistor of 2 ohms, and to the internal resistance to give us the total resistance now. So that means our total resistance is going to be the sum of these resistors. So RT is going to be 0,1 at this point, it's in series, plus RP is also in series, 1,636 at this point here, all these in series, plus 2 ohms, it's in series, plus the total of the internal resistance, which is 1,5. So you add everything. This is going to give us RT. All right, so RT, the total resistance is going to be 5,236 ohms. All right, so that is how you could have calculated the total resistance in this case. Then 7.22, the reading on the ammeter. The ammeter is for current. So what are they simply asking you is to calculate the total current, because this is where we have our ammeter here, and it is measuring the total current in the circuit. So the reading on the ammeter is simply the total current, because the ammeter, it reads current, okay? So that was the question. So the reading of the ammeter is total current, which is total voltage over total resistance in this case. So the total voltage is the total EMF that is of 9 volts. So we are going to divide 9 divide by the total resistance that we calculated of 5,236. All right, so that's our total current. In this case, if we divide properly, we obtain 1,71886, which is 1,71886 like this. So it's 1,719. If you round off to 3 decimal places, this is going to be 9 in amps. So we have got the total current. That's the reading on the ammeter. All right. The reading on the voltmeters V1 and V2. Okay, we've got voltmeters here. We have got V1, a voltmeter for the parallel combination that you have. So this one is simply the current, the total current that is flowing times the total resistance for the parallel combination. That's our V1. So that is, in this case, 7.23. So V1 is equal to VP, which is the total current times RP in this case. So that's V1. The total current, we calculated it now, it's 1,719 times the total resistance for the parallel combination, which is our RP, which was 1,636. So if we multiply these together, we are going to obtain 2,812 volts. That was our V1. All right, what about V2? V2 is a voltage. It's connected across 2 ohm resistor. So we're going to apply the 2 ohm resistor, but taking note, still the same current is going to flow through this of which is the total current. So our V2 in this case is going to be the total current times R2. So it is going to be times R2. So that's V2 is going to be the total current of 1,719 times that resistance. Sorry, the other 2 ohm, which is the 2 ohm in this case. So times 2, that's our V2 is going to be 3,438 volts in this case. All right, so we've got the voltages across the voltmeters V1 and V2. Then the last part of the question on 7.24 is to calculate the current through the 3 ohm resistor. So you have to check, where do we have the 3 ohm resistor? All right, the 3 ohm resistor is on the parallel combination. And what do we know about the parallel combination? We know that in a parallel circuit here, the voltage is the same, this V1. So we have got the voltage and the resistance. That means we can calculate the current. Okay, so we can calculate current from that, because we've got what? Voltage and resistance. So that means 7.24. So this is what you're going to have in this case on 7.24. So our current across the 3 ohm resistor is going to be the voltage across the parallel circuit, which is our VP, which is V1. So it is going to be V1 over R3 ohm in this case, of which the voltage across the parallel circuit, it was 2,812 divided by the 3 ohm resistor, which is 3. So that is the current in the 3 ohm resistor. Because current, the voltage the voltage in a parallel circuit is the same. As long you're in a parallel circuit, the voltage is the same. So that was the advantage. So if you divide these, you're going to obtain 0,937333 and so on. So which is going to be 0,937 amps. All right, so that was the current. Okay, so that was how we're supposed to obtain these guys. On question 8, which is on chemistry, we are now given name the 2 main groups into which elements are divided. So elements can be divided into metals and non-metals from our periodic table there. We've got metals and non-metals. These are the major groups that we have in this case, okay? 8.2, name 4 factors that influence the rate of corrosion in of iron, okay? If we are dealing with iron, what are the factors that affect the rate of corrosion? So we have got exposure to atmosphere. So you've got this exposure to atmosphere. There are so many, so you just list of your choice. Okay, exposure to atmosphere. Atmosphere. So if you've got any others, please mention them in the comment section. We've got also temperature variations. If temperatures varies, it increases. Okay. We also have pressure of presence of impurities on metals. Okay. So we've got presence. Is that the spelling, guys? No, this is supposed to be 1S there. So we've got presence, in this case, presence of impurities. Presence of impurities on the metal, all right? On the metal surfaces, all right? Such as the issue of acids and so forth, okay? Then also a composition between a metal and oxygen, okay? A composition of metal and oxygen. It can actually affect a lot this one, okay? It can actually influence the rate of corrosion of iron, okay? So that's what we have, guys. A total of 6 marks on this chemistry to mark a total of 100. So like I said, if you've got any others, mention them on the comment section so that we can also have them in our next classes. But for now, that's it, guys, for Mason African Motives. Till we meet again.